Good morning, everybody. Welcome to this session. In this session, we'll continue with AC circuit analysis. In the previous class, we did the circuit analysis for the pure resistive circuit, pure resistance, and connected to pure resistance connected to a voltage source, alternating voltage source, V is equal to Vm sin omega t. And we saw when we have the AC voltage connected to the resistor, the resulting current is also sinusoidal, and the resulting current is in phase with the applied voltage. So if applied voltage is V is equal to Vm sin omega t, and then the resulting current in the pure resistance is I is equal to Im sin omega t. So that is how, like, both the current and voltages are in phase in case of a pure resistance. So what is the meaning of that? Both will start with the same zero reference, and they both will reach the peak value at the same time. Both will become zero, again negative peak, and back to zero at the same time. So that is called as a both are in phase. And how do we draw the phasor diagram? Suppose if we have the voltage for the resistance on the same line, we are also representing the current. So in today's class, we will look into the pure inductance and pure capacitance, how the circuit will behave if we connect a pure inductor to a alternating voltage source. In the example, you can see we have an inductor having an inductance of L, and XL we will see it is called as a inductive reactance. So inductive reactance is the opposition that is offered to the flow of the current through the inductor, and L is the self-inductance. And what is self-inductance? It is the property of the inductor by virtue of which it opposes the change in the current. Okay, change in the current. The applied voltage is sinusoidal. That is why the current also changes with every instant, and inductance, it opposes that change. Okay, and during when it is current is changing, it opposes, and it creates a voltage which is given by the L di by dt. So it depends on the what is the change in the rate of change of the current. It is the voltage that will get induced, which will counterbalance the applied voltage. So the applied voltage is V is equal to Vm sin omega t. The back EMF or the voltage of the inductance. So whenever we are applying a alternating voltage to the inductor, I told you it will oppose the rate of change of current, and a back EMF or the voltage is developed across that inductor. That voltage is given by E is equal to L di by dt, and this E is exactly same as this voltage. Therefore, we can say the voltage across the inductance is equal to applied voltage. So whatever the voltage that is dropped across the inductance, that would be exactly equal to the applied voltage. From equation 1 and 2, we can say the E, lowercase e, is nothing but the voltage across the inductance or the back EMF is equal to the applied voltage V. So then substituting the E and V values, that is E is L di by dt is equal to Vm sin omega t. So if I take dt and L on the right hand side, what I will get? Vm sin omega t into dt divided by L. And if you see in this particular equation, Vm, what is Vm? Vm is the peak value of the applied voltage, that is constant, and self inductance for a particular inductor is also a constant. So Vm by L is constant. Now this is a small fraction of the current. If I want the instantaneous value of the current, then I have to integrate this equation on both the sides. Okay, so integrating on the left hand side of the equation gives integration of di is I, which is nothing but a instantaneous value of the current. On the right hand side, integration of Vm sin omega t divided by L into dt, and the integration of so Vm by L is constant, we take it out. Integration of sin omega t into dt is minus cos omega t. You have to see it is the integration is with respect to time, that is dt, minus cos omega t divided by omega, and we know that omega is also a constant. Omega is equal to 2 pi f, and that frequency is constant for a like I told you, in India the frequency of the alternating current, it is fixed, that is 50 hertz. So some countries they follow 60 hertz. So every country has a standard. In India we have the all the alternating electricity that is produced is at 50 hertz. Omega is constant, therefore we get Vm by L omega, and minus cos omega t can be represented as sin omega t minus pi by 2. The equation for instantaneous value of the current that is generated when we applied the alternating voltage to the inductor is given by this equation. I is equal to Vm by L omega sin omega t minus pi by 2. Now that is in the form of I is equal to Im. I is equal to Im. So this represents the peak value of the current, and sin omega t minus pi by 2. Therefore, the maximum value that can be attained by a sine function is 1. I will be maximum, that is when this sin omega t, this particular value is 1, then I is equal to the peak value. Therefore, we can say Im is equal to this is nothing but the Im is equal to Vm divided by L omega, or we can say also when we say Im is equal to Vm by L omega, if I divide the left hand side and right hand side by the root 2, Im by root 2 is nothing but the RMS value of the current, that is I. Vm by root 2 is nothing but the RMS value of the voltage. So we can represent Im is equal to Vm by L omega as in terms of a RMS value, that is I is equal to V by L omega, where this capital I and capital V are the RMS values. This equation 3 can be represented as I is equal to Im sin omega t minus pi by 2. So if we apply a voltage of V is equal to Vm sin omega t to the inductor, pure inductor having an inductance of L, the resulting current is I is equal to Im sin omega t minus pi by 2. So you can see now there is a phase difference between the applied voltage and the resulting current. And how much is the phase difference? The phase difference is pi by 2. If you draw the waveform, okay, the phase angle from equation 1, that is V is equal to Vm sin omega t, and equation 4, what is equation 4? I is equal to Im sin omega t minus pi by 2. So it is clear that current lags the voltage by angle pi by 2 or 90 degree. Why lags? You see minus pi by 2. It is lagging. It is current is behind the voltage. Means what? After we apply the current, after we apply the voltage to the inductor, it takes 90 degree or pi by 2 for the current to start. If you see the waveform here, this waveform, what you are seeing is V is equal to Vm sin omega V is equal to Vm sin omega t, that is the sinusoidal voltage that is applied, and the current. So this is the complete cycle from here to here. The total angle is 2 pi, half cycle is pi, 1/4 cycle is pi by 2. Now the current will start when the voltage reaches the peak value, right? When voltage reaches the peak value, slowly the current will start rising, and current will be maximum when the voltage becomes 0. Okay? Similarly, the when voltage reaches the negative peak, again the current will become zero. When voltage reaches zero, the current will become a maximum. So that is how we can see between this voltage and this current, we see a phase difference of pi by 2, and it is a lagging. So in case of an inductor, current lags the voltage by 90 degree, pi by 2. You have to remember that. Always in case of a pure inductor, current lags. How you can intuitively understand this is, when you are connecting a alternating voltage to the inductor, you apply the voltage. When this voltage is rising, so it will have a opposing factor on the inductor, and that is why initially there won't be any voltage. Once the voltage becomes maximum, then you will see the current will start rising. As the voltage drops, the slowly the current will increase. When the voltage becomes zero, then current will be the maximum. So that is how you can intuitively understand the current lags the voltage in case of a pure inductor. And mathematically, we represented V as Vm sin omega t, V is equal to Vm sin omega t, and I is equal to Im sin omega t minus pi by 2. And this is a waveform representation. Then the phasor representation. This is the on the top. If you want, you can have the phasor representation below the waveform. After the waveform, you can say. Now this is the voltage VL, that is the voltage across the inductor, and I is the resulting current. So I is this is the RMS value of the current. This is RMS value of the voltage across the inductance. You can see the current lags the voltage by 90 degree. So here this is the phasor for the current, and this is the phasor for voltage. Voltage is in line with the x-axis because it is the reference. It starts at the reference, and the phasor for the current, it lags by 90 degree. So you can just assume that it rotates like this phasor. When it rotates to 90 degree, then it will become zero. Then current will start rising, peak value, again it will become zero, then again minus peak value. Okay, and again it is zero. That is how we can interpret this phasor diagram. Now let us see what is the inductive reactance. As I told you, what is the inductive reactance? Inductive reactance is nothing but the opposition offered by the inductor to the flow of the current. Whenever we have the V by I ratio, whatever the value that we get, it is the opposition of the circuit to the flow of the current. From the above equations, we know that Im is equal to Vm by omega L, or it can be written as Vm by Im is equal to omega L. Vm by Im is equal to omega L, and also we know that Vm is directly proportional to the voltage. If I divide the numerator and denominator by root 2, then Vm by root 2 is nothing but the RMS value of the voltage. Im by root 2 is nothing but the RMS value of the current. Therefore, Vm by Im is equal to V by I is equal to omega L, and we also know omega I is nothing but the angular velocity. It can be represented as 2 pi f, and we know that V by I ratio is always a opposition, that is represented as XL. XL is the inductive reactance, that is the opposition offered by the inductive circuit, pure inductance to the flow of the current. Therefore, XL can be represented as omega L or 2 pi FL, and it is represented in ohms. You have to remember, in case of a pure resistance, V by I is R, that is the opposition offered by the resistor. In case of a inductive reactance, V by I is XL, and XL is the opposition by the inductive circuit, and both are represented in ohms. Now, to find what is the power consumed in a pure inductive circuit, first we have to find what is the power consumed in a for every instant. Okay, so we have to find at every instant what is the power consumed at every instant. Okay, from every instant on this we have to multiply it the instantaneous value of the voltage with the instantaneous value of the current, then we will get the instantaneous value of the power. Then we are going to integrate it over one cycle so that we can find out what is the average power that is consumed in the pure inductive circuit. So to find the instantaneous value of the power consumed, lowercase p is equal to v into I, and v is Vm sin omega t, I is Im sin omega t minus pi by 2. And sin omega t minus pi by 2 can be represented as minus cos omega t. So that is why you see the next equation, p is equal to minus Vm Im sin omega t into cos omega t. We multiply numerator and denominator by 2, and then we simplify 2 sin omega t into cos omega t is nothing but sin 2 omega t. What remains is p is equal to minus Vm Im by 2 sin 2 omega t. Now to calculate the average power over one cycle, we have to integrate this equation. This is the instantaneous value of the power. We have to integrate this equation from 0 to 2 pi, that is one cycle, with respect to d omega t, and divide by the total time period. What is the total time period? That is 2 pi. That is why 1 divided by 2 pi integration 0 to 2 pi p into d omega t, and p is nothing but minus Vm Im by 2 into sin omega t. So here you can see Vm is constant for the applied voltage, resulting current I is constant, the peak values are constant, 2 is constant. So all these things entities are constant. We integrate sine 2 omega t with respect to d omega t. So if you do this integration over one cycle, this will result as a 0. So if you do the calculation, you will get it as a 0. That is why p is equal to 0. Hence, the power absorbed by a pure inductance is always 0. In exam, they will ask you to do the circuit analysis of a circuit comprising of a pure inductor, or they can say prove that power absorbed in a pure inductance is 0. In both the questions, what you have to do is it is the same write-up. Any questions?
Sir, why sine 2 omega t is 0?
It's the integration you can do. That is not a problem. It is a simple integration. Or if you want detailed, I can share that as well. Okay. If you solve this particular sin 2 omega t with respect to d omega t, then you will get the answer as 0. Okay. So in the
Okay.
exam, you can just simplify that one. That is not an issue. Otherwise, we'll see in the next class. So now we completed a pure resistance and a pure inductance. So just to summarize, in pure resistance, if we apply a voltage, alternating voltage V is equal to Vm sin omega t, the resulting current is I is equal to Im sin omega t, and the Im is given by Vm by R. That is the value of the peak value of the current, and the voltage and current will be in phase, means both will start at the 0 reference. In case of a pure inductance, if we apply a voltage of V is equal to Vm sin omega t, the resulting current is I is equal to Im sin omega t minus pi by 2. So what is the meaning of that? In case of a pure inductance, current lags the voltage by 90 degree. And what is the power consumed in a pure inductance? The power consumed in a pure inductance is 0. Always you have to remember, whenever we talk about pure inductance, it does not consume any power. The power consumed is 0. And what is the power consumed in the pure resistance? We did that derivation in the previous class. That is P is equal to Vm Im divided by 2, or P is equal to V into I. V is the RMS value of the voltage and I is the RMS value of the current. Next, we will see a AC circuit containing a pure capacitance. As from the phasor diagram, you can already you can make out, in case of a capacitant, the current leads the voltage. Even before you apply the voltage, current will be there and it will lead the current, lead the voltage by 90 degree. So we will consider a circuit having a pure capacitance. So when we say pure capacitance and pure inductance, that means the any resistance part is that is not taken to consideration. It will just behave as a capacitance, nothing else. So in case of a pure capacitance, having a capacitance of C farad, and it will be having a capacitive reactance. So in case of a inductance, it is a inductive reactance, that is XL. In case of a capacitor, it is a capacitive reactance, represented as XC. XC is the opposition of the current. When we apply alternating voltage V is equal to Vm sin omega t to the current, which is also in sinusoidal form, and it is also alternating, represented as lowercase I. When we apply a voltage, consider an alternating current applied to a capacitor, the capacitance C farad as shown in the figure, then the applied voltage is presented as V is equal to Vm sin omega t. As a result of the voltage, current will flow in the circuit. Current will flow in the circuit, and here any instant. So the capacitance, the capacitor will start getting charged when you apply the voltage at any instant of the current in the circuit, that is I. Q be the charge on the capacitor plates. So the minute you connect the alternating voltage, the capacitor will start charging, and as the current is instantaneous, the amount of the charge is also instantaneous value, and that charge is represented by this equation. That is, if you want to find the what is the amount of the charge that is deposited, that is also instantaneous value, because it is keep on changing, because the voltage is changing, voltage is alternating, the amount of the charge that is on the capacitor will also change. That is given by Q is equal to C into V, where Q is the instantaneous value of the charge on the capacitor, C is the capacitance of the capacitor, which is constant for a given capacitor. For any given capacitor, we will have C as constants. Capacitance is constant, and V is the, it is a instantaneous value of the voltage. And we already know that the circuit current is nothing but the rate of flow of the electric charge, that can be represented as I is equal to dq by dt. Now we have this equation, Q is equal to C into V. If we differentiate both the sides, left hand side and right hand side, with respect to time, dq by dt, we, that is what, on both the side we are going to differentiate with respect to time. So left hand side we get it as dq by dt, and on the right hand side d by dt into c into v. So that is the right hand side, and here C is constant and V is what? V is Vm sin omega t. This alternating voltage, instantaneous value of the voltage, is represented by V is equal to Vm sin omega t. So we can write the equation as I is equal to capital C into dV by dt, and this V is nothing but Vm sin omega t. C is equal to I is equal to C into d by dt of Vm sin omega t, and we already know Vm is a constant, so we'll take that one also outside, and differentiation of the sin omega t is cos omega t into omega. Okay. Now this omega, again it's a constant. We can write I is equal to omega c Vm, then sine of omega t plus pi by 2. This cos omega t can be represented in terms of a sine, that is sine omega t plus pi by 2. Now if you remember what is the maximum value that can be taken by the this sine function, this can be maximum value is 1. So when this is 1, what is I is the peak value, that is Im is equal to omega c Vm. So this, in case of a capacitance, omega c into Vm represents the peak value of the current. Therefore we can write Im is equal to omega c into Vm, and the equation for the current is I is equal to Im sine omega t plus pi by 2. Now we have two equations. First equation is the applied voltage, that is V is equal to Vm sin omega t. 1 second, please hold on. Okay. Sorry, there was a background noise. That's why I had to interrupt. All right. Now, so this is the current equation, that is I is equal to Im sin omega t plus pi by 2. And so from equation 1 is V is equal to Vm sin omega t, that is nothing but the applied voltage. This is V is equal to Vm sin omega t, and we will compare the voltage with the current. And 4 is this one, I is equal to Im sin omega t. What we observe, we can conclude that current leads the voltage by an angle 90 degree as shown in the figure here. So therefore in case of a pure capacitance, current leads the voltage. Okay, current leads the voltage by pi by 2. If you see the waveform here, we have, this is the representation of the voltage waveform, that is V is equal to Vm sin omega t, so which starts from the 0. Now in case of a pure capacitance, we know this is the, it leads the voltage by 90 degree. So leads means when it is 0, when voltage is 0, the current is maximum, and when voltage is maximum, the current is 0. And similarly on the negative side, when again voltage becomes 0, current will be maximum in the opposite direction, and it will become 0 when voltage is maximum in the negative direction. So how we can understand this waveform intuitively is, the minute you connect the capacitor to the voltage source, that is at 0th time, what will already the capacitance is charged, it will start discharging, right? It will start discharging, and as the voltage starts increasing, the current will start dropping. The reason being, the voltage will start charging the capacitance. So when the voltage reaches the peak value, that is when the current completely stops. Okay, at this moment, pi by 2, the current almost stops, that is 0. And from the peak, the voltage starts reducing. When voltage starts reducing, again the capacitance will start discharging in the opposite direction. You can see it will start discharging in the opposite direction, and it will reach maximum as voltage is dropping. When voltage becomes 0, the current in the opposite direction is the maximum. Now what happens, now the voltage starts increasing in the negative direction, then slowly the current will start uh, uh, falling. So when the voltage reaches a negative peak value, then current will become 0 and so on. So that is how intuitively we can understand the current in case of a pure capacitance leads the voltage by an angle pi by 2. And the phasor diagram for that is, we have already saw that phasor diagram. So this is the voltage across the capacitance represented as Vc. This is the RMS value, and it is in x-axis because it is the starts from the zero reference. And you can see here current is leading. So current is leading by 90 degree. Why we have taken it on the top? Because if you remember the phasor in phasor representation we talked, we have to assume this as a rotating. This phasor representation is what? This represents the RMS value, and it rotates continuously with the speed of omega, angular speed of omega. So that is why it will rotate in the anti-clockwise direction, right? That is why the current I is having a phase difference of plus pi by 2. That is why we are showing it as on the top. So from with respect to V, the current is at 90 degree. The angle between the current and the voltage across the capacitance is 90 degree. So in case of a pure resistance, voltage and current are in phase, or angle between them is 0. In case of a pure inductance, the angle between the voltage and current is 90 degree, but current lags the voltage by 90 degree. In case of a pure capacitance, the angle between the voltage and current is 90 degree, and current leads the voltage by 90 degree. Now we will see what is the capacitive reactance. Okay, from the above equation number 4, okay, and from 3, we know that Im is equal to omega c Vm. We know that Im is equal to omega c into Vm. Then Vm by Im is equal to V by I. We know why. If you divide numerator and denominator by root 2, which is Vm by root 2 is nothing but the RMS value of the voltage. Therefore, Vm by Im is equal to V by I is equal to 1 by omega c. And omega is what? 2 pi f. This also is equal to 1 by 2 pi fc, which is nothing but the xc. What I told, the ratio of voltage and the current is always the opposition of the circuit. In the case of a capacitance, it is a capacitive reactance. Xc is equal to 1 by omega c is equal to 1 by 2 pi fc, and represented in ohms. R, XL and XC, they are represented in ohms because those are the opposition. Now you have to remember here the two formulas. XL is equal to 2 pi FL. To solve the problems, we have to remember these formulas, which will be very helpful. XL is equal to 2 pi FL, and when you are doing XC, it is 1 upon 2 pi fc. So 1 divided by 2 pi fc. The maximum mistakes I have seen is like XL is equal to 2 pi fl, and similarly they forget, they say XC is equal to 2 pi fc. That is wrong. XC is equal to 1 divided by 2 pi fc. Please remember that. Now, what is the power that is consumed in the pure capacitance? It is 0. Okay, remember, power consumed in the resistance is P is equal to V into I. V, okay. In case of a pure resistance, the power consumed is P is equal to capital V into capital I. That is RMS value of the voltage into RMS value of the current I. In case of a pure inductance, the power consumed is 0. In case of a pure capacitance, the power consumed is 0. Okay, now to find the what is the power consumed in the capacitance, this is the instantaneous power consumed is equal to V into I, where it is a instantaneous voltage and into instantaneous current. V is Vm sin omega t and I is Im sin omega t plus pi by 2. And sin omega t plus pi by 2 can be represented as cos omega t. And if you multiply this one by 2, 2 into sin omega t into cos omega t is sin 2 omega t. Therefore, instantaneous value of the P is given by Vm into Im divided by 2 into sin 2 omega t. And now we have to find the average power consumed in one cycle. This is the instantaneous power consumption. If you want to find what is the average power consumed over one cycle, then we have to integrate this equation 0 to 2 pi and divided by 2 pi. So here again this P is nothing but Vm Im by 2 into sin 2 omega t. Vm Im is constant, so we take it on the left hand side, and the integration of 0 to 2 pi sin 2 omega t. If you do the integration, you will get the value as this value as 0. So therefore power consumed in a pure capacitance is 0. And just to represent this sine to omega t, we know sine omega t, right? I will show you the waveform. Just intuitively we will understand why it is 0. This is sine omega t. V is equal to Vm sine omega t. Okay, when I say sine 2 omega t, frequency is doubled. Means what? Frequency is doubled means what? Let us say we have 50 hertz. Means what? 50 hertz is there are 50 cycles in 1 second. If I say 100 hertz, 100 hertz means what? There are 100 cycles in 1 second. This V is sin omega t, right? V is equal to Vm sin omega t. Now what is the equation we are getting for power? For the power we are getting the equation as Vm Im by 2 some constant. Okay, you can say Pm into sin 2 omega t. The frequency is a double. When frequency is double, you can see this is the power, whatever the shaded waveform you are seeing, that is the power waveform. So the power has two cycles in one cycle of the voltage, and we know that this is a symmetrical waveform. In case of a symmetrical waveform, what is the average value? Average value over one cycle is 0. Means you can see the power has two positive cycles which are exactly equal as two negative cycles. So that is the reason power is 0. That is with representation of the waveform. But if you solve this, if you simplify this integration, you will get the answer as 0.